this video, we are going to be discussing Maxwell's equations and how we can use Maxwell's equations to verify the existence of electromagnetic waves. And I've been very much looking forward to making this video because honestly, this is what's at the crux of electromagnetism. It's the bringing together of electricity and magnetism. And completely inconsequentially from that, we find that we get light as a completely emergent property of the equations, which I think is really, really awesome. Before we get into it, let's just revisit what we've done up till this point. So to start with, we discussed electrostatics, where we derived Gauss's law, which relates the electric field to any charge within space. And then we looked at magnetism, and that magnetism resulted from essentially charges moving. And from that, we actually found that there could not exist any magnetic monopoles in space. That is to say that the divergence of B is equal to 0. Then we had a look at what happened with currents, and from currents we found that there was a magnetic field induced as a result from a current flowing in the wire, which is known as Ampere's law. If we reverse the situation, we find that whenever we have a changing magnetic field, then you get an induced EMF, which therefore induces a current to flow within the wire. So far so good. But there is in fact one major problem with one of the 4 laws. And to fix it, let's go ahead and jump right into what this is all about. So these are the 4 equations that we have successfully managed to derive and can predict all sorts of various different phenomena occurring within electromagnetism. You essentially start with these equations and then use the various situations. And from this, you can get loads. But there is one of these equations is a problem. And in fact, it is this equation right here. Ampere's law is the culprit. And it's not immediately obvious why that should be the case. Because of course, it seems very similar in a sense to Gauss's law. We have the derivative of a field giving some kind of density of charge. And in this case, we have a derivative of the magnetic field giving some kind of current density. And since magnetic fields arise from changing point charges, then that should make sense, right? Well, the problem comes when we apply the divergence to this equation right here. So let's go ahead and take the divergence of both sides of Ampere's law. So we are going to get the divergence of the curl of B is equal to the divergence of mu naught J right here. Now, the key point is that this has to equal 0. The divergence of the curl of any vector is equal to 0. And this is a mathematical identity, but you can also kind of make sense of it just thinking that if you take curl of 2 vectors right here, you produce a vector that is at right angles to those 2 vectors. But if you take the dot product right here between this new vector that's formed and any one of these 2 vectors, then you'll just get 0 because of course it's at right angles. So essentially this should always equal 0. And from that you can say that this must equal 0 right here. And well, we know mu naught isn't equal to 0. So this is essentially saying that the divergence of J is equal to 0. And this isn't true generally. The divergence of J is a specific case for electrostatics, and what we actually derived was that more generally the divergence of J we said is equal to minus d rho by dt. This is the continuity equation, and this divergence of J being equal to 0 is only one very specific case of the continuity equation. And so if this is equal to 0 according to Ampere's law as it is at the moment, then that must mean that this is equal to 0. And so if d rho by dt is equal to 0, then that must mean that you're only dealing with a steady state problem. And that is only a very small portion of problems in electrostatics. So how do we fix this? Well, let's go ahead and look at the continuity equation. So we have that the divergence of J is equal to minus d rho by dt right here. That's what we said. But what is this rho right here? This rho we can actually get from Gauss's law, because of course the divergence of E is equal to rho over epsilon naught. And so we can just rearrange this for rho. And so when we do that, we get that rho is equal to epsilon naught times the divergence of E right here. So we can go ahead and substitute that into the continuity equation. And so when we do that, we get this equation right here. And what we can actually do is, like we've done many times before, just reverse the order of the spatial derivative and the time derivative. And we can just simply rewrite this hand side of the equation as being equal to minus the divergence of epsilon naught dE by dt right here. And I'm going to add this right-hand side to both sides of the equation. So essentially, I'm just going to try and make the right-hand side equal to 0. So we get divergence of j plus the divergence of epsilon naught dE by dt is equal to 0 right here. And of course, we've got two divergence terms, so we can just factor these in. So now, if we notice, rather than just simply saying that the divergence of j is equal to 0, which is only one very specific case, when we apply the continuity equation, we get the result that this divergence of j plus this extra term right here is equal to 0 right here. And this is basically the key thing, because this second term right here will account for this vector identity problem. So if we say that the curl of B, rather than being equal to mu naught j, we say it's mu naught, and instead of j, we've got this term right here, multiplied by j plus epsilon naught dE by dt. When we take the divergence of both sides, then this side will be satisfied due to the fact that any vector has to be satisfied by that relationship. But this equation will now also be satisfied thanks to the continuity equation, thanks to the flowing of charge. And so this right here is the fixed version of Ampere's law. And this is just known as the Maxwell-Ampere law. And basically it includes this extra term right here. And that extra term accounts for this vector identity mathematical problem right here. And this is the final version of Ampere's law and is Maxwell's fourth and final equation. And one thing to note is that this equation, much like Gauss's law, will also have a version in materials. So in the material case, we said that curl of H, where H is the magnetic intensity, is equal to J right here. But that was Ampere's law, and so that also won't satisfy the vector identity that the divergence of curl has to equal 0. And so you get this extra term, which is dd by dt right here. And this is applying Gauss's law in a material. So this is Maxwell's fourth equation in a material right here. Now, one other way to think about this equation, which is less mathematical, is to think about it in terms of Stokes's law, because essentially you have this curl term right here, and so therefore there's going to be a relationship to Stokes's law. So what we said with Ampere's law was that you can construct a essentially surface around the current that's flowing, and as long as this surface is bound by this loop right here, so it doesn't matter whether it's like a bag or something like this, then you can construct any surface, and you know that the magnetic field produced around this ring right here is related to the current that flows through the surface. And that would apply for any surface. So this random bag right here, oftentimes we choose it for convenience sake. It's much more convenient to choose a circle like this, but technically you can choose any surface you want. Now, the way this problem is often illustrated is if you put a capacitor right here. So this is our current flowing right here, and we have this capacitor in the way. And the important thing to note is that no current flows through a capacitor. It's essentially a gap in the circuit where both charge and therefore potential difference can be stored right here in this electric field in the capacitor. So what happens when we have this loop right here? We have our Amperian surface. And what happens if we decide to put this surface in between the capacitor? Now, albeit this is a very specific problem, and although this is somewhat crude because of course you would not typically choose to do that, but in theory you could, because of course Stokes's law said that you can have any surface as long as it's bound by this ring right here. Well, we can see that no current flows through this capacitor at all. But from Ampere's law, as we had it before, that would tell us that there is no magnetic field, because if there's no current, then there's no magnetic field in the ring. And that's crazy, because of course we have a current that's flowing, we know the current's flowing, and how can there not be a magnetic field if there's a current flowing? Just because this surface right here doesn't happen to be at the right point, that doesn't mean there isn't a magnetic field, because if we put our surface here, then of course we would find a magnetic field because there's current penetrating the surface. And so what you can essentially think of this extra term as an implied current. So there is a current there that's going through there, but it's an implied current, and that is often called the displacement current, and it's related to the rate of change of the electric field right there. So that is an alternative way of visualizing the problem with Ampere's law and how you can use the displacement current introduced by Maxwell in order to remedy that right there. So here we have it. These are all of Maxwell's equations. And as we can see, there is a really nice symmetry going on with some of them. So we know that both of them are the divergences and two of them are curls. This one is just completely describing the electric field, and this one is just completely describing the magnetic field. But these two right here actually link the electric and magnetic fields. And this is all thanks to the displacement term, which actually relates the rate of change of the electric field to the magnetic field. And it's these equations that essentially you can derive the entire theory of electromagnetism from. So name absolutely anything, and of course you need to know a few different definition relationships. But essentially this is where it all comes from. And likewise, if you're in a material right here where you may have free charge and free current flowing, but that might be affected by the material in which you're measuring it in, then you use these equations right here. Now, I am going to completely shift gears a bit now, and I am going to talk about waves. And some of you might already know why I'm talking about waves. In fact, I've kind of been hinting at it a lot. I'm going to completely break away from Maxwell's equations for now. And so what I want to draw is I want to draw just a graph of a wave. So hopefully you guys have seen this sort of graph before. This is going to be showing the spatial distribution or position of the wave. And this right here is going to measure the height of the wave, and it's going to be a function of the position. And I'm going to take it at a snapshot in time right here. So this is going to be at the t=0 mark. So this is right before we start the stopwatch. This is going to be a snapshot in time. And it's going to look something a little bit like this right here. So it doesn't really matter. It's going to have like a peak there or something going on, and then it's going to have the exact same peak like here. So it's a coherent wave, and we're going to say that it's going to be traveling in this direction right here. So it's going to be traveling in the positive x direction. So what is going to happen after a certain amount of time has elapsed? Well, as I said, if it's traveling in this direction, then all that's going to happen is that it's going to have moved to the right. And so we're going to end up with a graph that looks a little bit like this right here, because there's going to be a shift in the displacements of the two peaks, and that's going to happen after a time t. And for now, we are going to say that the velocity in which the wave is traveling is a constant right here. So it's not accelerating or decelerating. Now, I am going to call the distance in which the wave has moved from here to here, this is going to be a distance d right here. So this is just how far, say, a peak, if you were to measure, has moved after a time t. But when we are graphing mathematical functions, we can actually express a offset or a shift of a certain distance as being equal to a subtraction within the function. So say if you have y=x² right here, and then we just draw this really simple graph. So it's going to look something like this. If we want to plot the equation y = say x+3² right here, just as an easy example, then we know that when x is minus 3, then y is equal to 0, because minus 3 plus 3 is 0, 0 squared is 0, and so therefore y is equal to 0. And so what you end up is, if you plot a graph like that, is you just get the same curve, but just shifted to the left by 3. So this is going to be at the point minus 3, 0, right here. So that's just an easy example, and we've got the same thing kind of going on right here. This is just a shift of d. And so what we can write is that we can write that the h, which is our kind of height profile right here, at x and t, so this is the second curve that we drew, the second graph, is equal to h of x minus d right here, because of course we're shifting to the right, and so if we shift to the right we actually do minus d at time equals 0 right here. But what is this distance d? Well, we can just express the distance as equal to the product of the velocity of the wave, because we said it's traveling at constant velocity, times the time elapsed. So this is equal to h of x minus vt at time equals 0. And what we've essentially done is we've kind of changed this function from being a function of two arguments, x and t, to just being a function of this x minus vt variable right here, which is only one variable essentially. And so we can write this as being equal to a different function, let's just call it f for now, of x minus vt. And we can call this new variable x minus vt just being equal to u right here. So function of u where u is equal to x minus vt. Now, what I'm going to do is I'm going to start taking a bunch of derivatives of this function f right here. And when we do that, we end up with a really awesome result. And it's actually one of the most important equations in all of physics. So let's go ahead and do time derivatives. And we are going to be employing the chain rule in order to make these derivatives right here. So what is the derivative of this f right here? Because we've now just made it one function, so we don't have to worry about h anymore, with respect to time. Well, df by dt, if we use the chain rule, is equal to df by du times du by dt, right here. So let's go ahead and substitute that in. What's df by du? Well, we don't really know what the function could be, so we'll just leave it as df by du. But du by dt, we do know what that is. That is just equal to minus v right here, because of course x is a constant, and the derivative of minus vt is just minus v right here. Cool. And now I'm going to take the second derivative, and there is a really interesting reason why we have to take the second derivative and we can't just stop at the first derivative, and I will provide a link to that in the description. So this is going to be d2f by dt squared, and this is going to be equal to, well, just doing exactly what we did before. So this is going to be the derivative of all of this with respect to u multiplied by the u derivative yet again. So we're going to get minus v times the second derivative of f with respect to u multiplied by another factor of minus v right here, thanks to the chain rule. And these minus v's are just going to combine to give a v squared right here. And so we can rearrange this quite easily to just give that the second derivative of f with respect to u is equal to 1 over v squared times the second derivative of f with respect to t, right here. Cool. So that was the time case, and let's do exactly the same but with the spatial dimension right here. So let's do, instead of df by dt, we're going to do df by dx right here. And like we said before, this is going to be equal to df by du times du by dx. So df by du we don't really know, so we'll just leave that as it is. And du by dx is just, well, that's just 1, because of course this part isn't a function of x, and this, when you differentiate, is just going to be equal 1. So that's just going to be 1. So we get that df by dx is just exactly the same as df by du right here. And so if we take the second derivative of both sides, we just differentiate yet again to give this right here. But we've already derived what d2f by du squared is right there. And so therefore we can equate this to this right here. And so we get that the second derivative of this f with respect to x is equal to 1 over v squared multiplied by the second derivative of f with respect to t right here. And this is a really awesome equation, and we call this the wave equation right here. And it's one of the most important equations in physics, like I said. And basically what it's telling us is that if you have a function f right here, then this equation kind of verifies that this function f could be a wave equation, because of course we stated that the condition for a wave equation is that after a time t, the wave will have periodically shifted right here. And so any wave must live up to this wave equation right here. Now this is in fact the one-dimensional wave equation. Because of course we're working in 3 dimensions, instead of writing the second derivative of f with respect to x, we actually write the del squared of f, which is sometimes called the Laplacian, is equal to 1 over v squared times the second derivative of f with respect to time right here. And so this is the more general wave equation in 3 dimensions. And of course, whenever you have del squared, that will depend on what kind of geometry you're working in. So if you're working in spherical coordinates, then you would obviously use the spherical case. Same goes with cylindrical or any other coordinate system you care to mention. So there we go. That is the wave equation. Now, here comes the awesome bit. Let's go to Maxwell's third equation, that the curl of E is equal to minus dB by dt right here. So Maxwell's third equation, that's good. And what we're going to do is we are going to take the curl of both sides of this equation. So we're going to get the curl of E is equal to the curl of minus dB by dt. And whenever we have a double curl, we use the vector identity that the curl of a vector is equal to the gradient of the divergence minus the Laplacian right here. So let's go ahead and substitute that into the left-hand side of the equation. And what we can do is we can put the curl of this right-hand side of the equation inside the derivative. So we're going to get the time derivative, or minus the time derivative, of curl B. And now what we're going to do is we're going to substitute in Gauss's law to the left-hand side of the equation and Ampere's law to the right-hand side of the equation. And the reason we're going to do that is because we have a divergence of E on the left-hand side and a curl B on the right-hand side. So when we do that, we are going to get this right here. Now, what happens in a vacuum? Well, like I said, in a vacuum, we don't have any free charge right here. There is zero charge density in space at all. And we also have zero current right here. So this J is going to be 0. So both rho and J are going to be equal to 0 in this case. And so therefore we are going to get that 2 of these terms are going to disappear. And so what we're left with is this right here. So the Laplacian of the electric field is equal to mu naught epsilon naught times the time derivative of the electric field. And so tidying this up a little bit, we get this right here. But what is this? This is literally just what we derived as the wave equation. We have the second spatial derivative is being equal to a constant right here times the second time derivative right here. And this is massive because out of just doing some small manipulations and some substitutions, we get that the electric field satisfies a wave equation right here. And so let's go ahead and compare this to the wave equation we had before. So we have this 1 over v squared in this equation right here and mu naught epsilon naught in this equation right here. Now, let's bear in mind, mu naught and epsilon naught are empirically determined constants that were known about for many years and had been measured using the experiments on electricity and magnetism at the time. But we are suggesting that this mu naught epsilon naught could be a 1 over v squared right here, because it kind of fits as the coefficient in the wave equation. We have a wave equation right here. We know we do because we have the second spatial derivative being proportional to the second temporal derivative. And so what we can do is we can identify this mu naught epsilon naught as being equal to 1 divided by v squared. And so if we rearrange this, we get that v is equal to 1 divided by the square root of mu naught epsilon naught. And so we have the speed right here. And this we call c, and we obviously know what c is. C is the speed of light. It is the speed of electromagnetic radiation. And therefore we have just proven that light is an electromagnetic wave that propagates at velocity 1 divided by the square root of mu naught epsilon naught, which we define as c. And when you work out what c is, you get that it is equal to 299,792,458 meters per second right here. But more commonly, you'll just see this very much rounded up to 300 million, or 3 times 10 to the 8 meters per second right here. And so there we go. We have this speed that's just kind of popped out of nothing but electricity and magnetism. And we have waves which are propagating with a characteristic speed that is determined by nothing else other than empirical constants that were observed hundreds of years ago. And I think that is really, really awesome. And so that was probably one of physics's biggest moments in all of history. And so therefore we now have a clearer idea of what light actually is. And so we know that light is an electromagnetic wave which propagates at a singular speed of 3 times 10 to the 8 meters per second. And so this shows that electromagnetic waves can propagate through a vacuum at a speed of c right here. So with that huge result out of the way, in the next video we are going to be solving this wave equation right here, and we are going to be talking about the energy that is contained within these electromagnetic waves of light right here. So see you guys in the next video. Take care.